All right, today we're going to talk a little again about chemical bonding, but today we're going to focus in on metallic bonds. And we're going to keep this one real simple. We're not going to get into all the details of metallic bonding and for purposes of the test and for understanding for this chapter. Mainly this chapter, when we talk about chemical bonding, we'll focus in on ionic bonds and covalent bonds. That'll be the big deal. But we do want to mention metallic bonds because there's some rather fascinating and intriguing things that go along with metallic bonds. So first of all, understand this. As we talk about metallic bonds, we're not talking about a single atom or two atoms. It takes an abundance of atoms to create what we call metallic bonding. And this can be it can be several different types of metals bonding together, or it can be, let's say you have a bar of iron. Within that bar of iron, you would have trillions upon trillions of atoms of iron, and they are all bonding with each other. So it can be something as simple as that, is just a chunk of iron that you have that's not necessarily in any shape, it's just there. Those atoms are bonding with each other. So it does not have to be one iron atom bonding with a copper atom or a copper atom bonding with a gold atom. It can be just a single type of element like iron or like copper bonding with itself as you have a sizable amount or a large number of atoms. So that's kind of what we're going to be focusing in on. Make sure that you understand that we have a large number of atoms here that in this process as we go about describing this. The best way that scientists have come up with to describe this is what's called the electron sea theory, because basically you end up with a sea of electrons, as we're going to see here in a minute. And we start off with something that we have learned when we talked about ionic bonding, is that metals tend to give off electrons because they have a low ionization energy. And because they have a low ionization energy, it's very easy for them to give off electrons. And they don't want to receive electrons, so they get rid of their electrons to complete their valence shell. But as we found out when we talked about ionic bonds, when metals give off electrons, metals end up being positive. They become positive atoms, or what we call cations. So you have all these metal atoms. So let's say a bar of iron. You have all these iron atoms, and they've given off their electrons, whether that's two valence electrons or three valence electrons. They give off those valence electrons and then disperse them out into this mass sea of electrons. And so now what you have are a bunch of positive ions or cations. And it creates a sea of flowing free-floating electrons, and we sometimes refer to these free-floating electrons as delocalized electrons. You might want to remember that term. That might be something important for the test. We'll see that again in later chapters, this concept of delocalized electrons. In other words, they're not attached to any particular atom. They're free to roam from atom to atom, which is different from an ionic bond, or later on when we talk about covalent bonding, where that particular electron belongs to a specific atom and is held there, okay, by either electrostatic attraction in an ionic bond, or in a covalent bond, you've got both atoms sharing and pulling on that particular electron. That's not the case with metallic bonding. Metallic bonding is very different. You have these electrons, they're given off, and they're just kind of floating out there. And it creates a cation, and so the cation is positive, so you have all these positive atoms, okay, metal atoms, and around them you have all these negative electrons. And of course, the electrons being negative, we've talked about before that electrons repel each other. And so they're going to repel each other, but they're also going to be attracted to the cations. So you have this sea of electrons floating around that are repelling each other, but they're also attracted to the cations. And so as they move around, the sea of electrons, and again, these electrons are moving independently of each other. It's not like they're all moving as a group, because remember, they repel each other. So all of these electrons, trillions upon trillions of them, are floating by each atom, and as they pass by, they're temporarily attracted to the cation, but they don't stay there. They're not attached to that atom. And so as they pass by, they temporarily, more or less, complete its valence shell before moving on. And so in that sense, the valence shell is always full, and yet it creates a very unique situation. So we're going to kind of illustrate what goes on. So if this is a piece of metal here, and the positives there represent the large atoms, and they're the cations. They've given off all of these electrons. These electrons are not attached to any particular atom, and as we're going to see, they're going to kind of just wander through here. So there's this massive sea of electrons, and they're going to wander through this atom. So let's play this kind of illustration here. You see that the electrons are just kind of going here, there, and everywhere. They're not bound to any one atom. They're loose, or what we call delocalized. So let's play that again so you guys can see it one more time. And we have the electrons kind of going around, and they're not orbiting around any one specific atom. They're wandering all over the place as they pass through this mass or maze of positively charged metal ions, basically. And what this does, because the unique thing that this creates for metals, because these electrons are not attached to any particular atom, what this creates is when we talk about metals being conductive. Okay, they can conduct electricity, they conduct heat, and other physical properties that we talked about earlier this year, like malleability and ductility. We're going to focus on conductivity just because it's probably the easiest to kind of grab hold of. Is because these electrons are loose, if you zap it with energy, whether that energy be electricity, whether that energy be heat on one end, why on the other end will it conduct that electricity through the metal? Because the electrons are loose, and the electrons carry that energy, and as they bump into each other, they can transport that energy from one end of the substance where all the atoms are on one end. So if you think of, let's say, on the right side of this here with these atoms on the right side, if that's one end of the bar of iron that we have, or whatever metal you want to choose, let's say it's iron or copper, and we zap it with electricity, because all of these electrons are loose, they're going to transport that energy from one end to the other. If those electrons were tightly bound and attached to one particular atom, then that energy would not necessarily get transported to the next atom and on down the line, and having this kind of domino effect till you get to the end. Instead, that atom might get energized, and maybe even that electron might be forced to leave the atom, but it wouldn't necessarily transport that energy all the way on down the line. And so that's why metals make excellent conductors. Now, some are better than others, but in general, metals conduct electricity. And so because those electrons are free floating, or because they're loose and not attached to any particular atom. So that's kind of the basics behind what we call the electron theory, or behind metallic bonding. We're not going to go into a lot more detail than that. That's the basics of what I want you to understand in class. And we will deal with in class a little bit more and discuss those things. Again, if you have any questions, make sure that you write those down, and we'll deal with those in class when we get there.